A federated building model is a collision zone. It is the precise coordinate space where competing engineering disciplines, spatial constraints, and legal liabilities intersect. This dashboard displays an aggregated clash report. It tracks exactly 1,795 unresolved physical conflicts across a single building tier. In a traditional 2D workflow, discovering these intersections on the job site means tearing down installed work, scrapping materials, and absorbing massive schedule delays. An enterprise building information model computationally forces every spatial conflict to the surface months before the first steel is poured. Moving a primary ventilation duct that pierces a load-bearing beam involves a complex chain of technical and procedural dependencies. To clear this single intersection, we have to look past the 3D geometry and untangle the invisible layers of data that actually define these objects. Every digital twin operates within a foundational framework of legal contracts and execution plans. When an engineer uploads their design into a federated model, they do not surrender their intellectual property rights, nor do they transfer their legal liability to the other project stakeholders. Documents like the BIM particular conditions draw a strict contractual boundary around every element. This ensures that the risk associated with any piece of geometry remains tied exclusively to its original author. Conflicts are resolved using level of detail, or LOD, defining an element's legal reliability. The beam is LOD 400, functionally locked with precise instructions. The duct is LOD 200, a schematic requirement. Because the beam has higher contractual reliance, the duct must move. If an inconsistency persists, the ultimate failsafe is the contract. Traditional 2D drawings supersede the 3D model in a dispute, unless the execution plan specifically designates the data as the final design model. The contractual hierarchy of LOD and risk allocation dictates who bears the cost and responsibility of manipulating a vertex on screen. This raises a practical question. Why did the mechanical engineer route the duct directly through a primary structural beam to begin with? The mechanical engineer did not manually draft that geometry. The duct's dimensions are generated algorithmically, driven by the spatial parameters of the building. The software computationally analyzes the bounded architectural rooms. It extracts variables like intended occupancy schedules, lighting density, and latent heat gains. This localized spatial data is exported into a GBXML format to run thermodynamic energy analyses. This graph shows the output, dictating rigid cooling requirements, a mandatory 1,011 liters per second of airflow to condition the target zone. The BIM platform uses this target to drive an automated duct sizing algorithm, but it is constrained by limits. It cannot exceed a maximum friction loss rate of 1.00 pascals per meter and is capped at 5.1 meters per second. The engineer cannot shrink the height of the duct to slip it underneath the structural beam. Doing so would choke the airflow and violate those friction and velocity constraints. The duct's position is a calculation of thermodynamic requirements. Managing these competing legal and physical constraints requires a centralized operational framework, the common data environment. Merging multidisciplinary models into the CDE demands absolute data hygiene to prevent system-wide indexing failures. This layout details the required file naming standards. Every file follows an exact syntax, passing sequentially through variables for project, company, discipline, zone, and level. This structure is fragile. A single missing underscore or an incorrect subdiscipline abbreviation immediately breaks the CDE's ability to automate clash detection. Heavy native authoring files are passed through a digital filter, stripping away unnecessary drafting metadata. They are exported into lightweight cache files, allowing rapid computational processing. These optimized files are then compiled and interlocked, generating the federated model. Without this standardized architecture, the digital twin collapses into an uncoordinated data swamp. With the federated model assembled, the team executes the automated clash detection rule sets. Before the server runs the check, the BIM manager defines a spatial tolerance, setting an absolute hard clearance requirement of 0.010 meters. This chart illustrates the spatial triage system. Minor clashes under 50 millimeters are solved internally. Mid-clashes between 50 and 100 millimeters require cross-disciplinary discussion. Major clashes over 100 millimeters trigger formal intervention, executive review, and redesign. Our mechanical duct piercing the structural beam qualifies as a major clash, triggering a formal review process within the CDE. To ensure clarity, the coordinator generates a save viewpoint. This locks a specific XYZ coordinate matrix, guaranteeing stakeholders examine the exact same spatial data. This triaged coordination protocol transforms an overwhelming 1,795-item clash report into a systematic engineering workflow. To bypass the structural boundary, the mechanical engineer splits the single duct into 2 parallel runs, routing them dynamically around the steel beam. As the duct splits, its internal friction loss parameters update. The simulation confirms the new pathway remains legally and thermodynamically compliant. The clash is resolved through the synthesis of contractual boundaries, applied physics, and data protocols. Resolving these collisions clears the path toward the project's ultimate goal, driving the federated model to LOD 500, which represents the verified as-built condition. At LOD 500, the model functions as a 6D and 7D facility management database. The digital model connects directly to physical execution on site. Digital inspections systematically map the constructed physical elements directly back into the database. Building information modeling is a data standard. Master the computational architecture and the legal constraints, and the physical geometry will flawlessly follow.